All right, so we want to talk today about how to use more than just prototyping and random trial and error to design snap fits with 3D printed materials. And we're going to start with just understanding some of the material properties before we get into a couple different ways you might want to have an elastic snap fit operate and some of the analytical considerations that can help support your prototyping. So fused deposition modeling, so FDM, 3D printed materials, both do and do not behave like textbook elastic materials. Let me explain to you what I mean by that. Well, we need to see what a textbook material looks like, and frequently that means looking at metals. And the plot on the right is called a stress strain curve. And if you haven't seen it before, let me break down what the axes mean. So on the horizontal axis is strain. And strain, in maybe just not so many words, is how much you stretch a material. So how much you pull it and stretch it, or you push it and stretch it by compressing it, or bend it or twist it. When you're doing those things, the material is stretching. And strain is a way to measure that amount of stretch of the material. Even for materials like metal, they are stretching. And then stress, the vertical axis, is just force over area. And the important thing to know about stress is that it's the thing that actually leads to a part failing or breaking. So as we walk through this diagram a little bit from left to right, it says that as you strain a material, the more you kind of, stretch that material, the stress goes up. And not only that, it goes up in a linear fashion. Interestingly, in this whole region, as you stretch the material, if you release the material, it goes back to its original shape. So this is called the elastic region because it behaves just like a rubber band would behave in the sense that you pull on it or you twist it or whatever, and then it just goes back to its original position once you let go of it. Now, when you get past that, so past the yield strength, which is measured by stress, it gets into a region where the part hadn't broken yet, but it's deformed. It's not going to return to its original shape. Like when you bend a coat hanger and it stays in a new shape, right? Hadn't broken yet and it isn't about to break, but it's not going to spring back to its original shape if you push it too much. And then if you go past that, it's where the material is really starting to fail and ultimately leads to failure. So thinking about this linear region back to the left, if we're talking about snap fits, that's the area we're talking about because we want this thing to bend and then bend back to its original shape or flex and flex back to its original shape. One thing that you'll notice here by saying it's linear is that, um, for every amount of strain that you put on it, for every unit of strain, the stress increases by the same amount. And that change in stress per unit of strain is just the slope of that linear region. And it's called, as you can see here, Young's modulus, or sometimes elastic modulus is used for that. And you can go look up elastic modulus in tables, in books, or on the internet. All right, I said this is for metals. Well, we're not 3D printing metal in this case. What does this stress strain curve look like for plastics? And plastics come in all sorts of different ways that they behave. An elastomer on the bottom is like rubber. So as you strain it more and more, it just sort of, has a little bit of stress in it, but it can keep, it's not going to break, for a long, long time. It's going to stretch for a long time. And then you go up to the other extreme and it's a brittle plastic. where it looks like all it has is that linear region from the plot for metals, from the stress strain curve for metals. And it turns out that polylactic acid, the type of plastic that we'll 3D print with, it is a brittle plastic when it's below 45 degrees Celsius, which it's going to be once the part has been formed, right? Um, and so that's another interesting reality is that, stress strain curves are different for different temperatures, not that relevant for this project. Outside of really what's relevant is that, that polylactic acid, it's going to behave like this green curve here, which is pretty much linear. And then it just breaks. It doesn't have that region where it bends but doesn't break, um, like we saw for metals. And you could look up in a book what the tensile strength or the flexural strength is of a brittle plastic, and that's that point at the very top where it fails. So a typical workflow for analyzing if a part will break from being overloaded is determine the strain and or the forces, because those are related to each other. But let's just say strain, because that's what we've talked about so far. And then you look up the elastic modulus, the Young's modulus from the material, and there are tables that list this, like I've said. And you use that value for Young's modulus and a few other things to calculate the stress. And then you determine if the part will break. Is the stress over the yield stress if it behaves like a metal? Or in the case of the PLA, is the stress less than the tensile strength of the material? Tensile strength is measured in stress. Or if you're bending it, the flexural strength of the material. And if yes, if the part will break, then change the dimensions or change the materials for the given loadings, if you can't change those, so that the part won't break. Um, or if you determine you calculate it and it won't break, then well, how far away is it from breaking? And is it, and that's called the safety factor. Okay, a big assumption in all of this so far is that the elastic modulus, Young's modulus, E, is the same regardless of the orientation of the material. This kind of property is called, if a material has this property, it's isotropic. And most metals, when you're working with metals, are generally considered isotropic materials. The orientation of the metal doesn't change the properties of it. Most metals. For 3D printed parts, this is clearly not true, and they're called anisotropic. And there's several reasons for this. One is that we're printing them in layers. And if you have a beam that you're putting a force on like this, and you can see how I've kind of drawn the layers, if you 3D printed the part that way versus 3D printed the part with the layers in the other orientation, you're going to get a different point of failure, different stress of failure. And then those are not equivalent to each other when you're looking at this, the stress in the part for a given strain. And then secondly, the infill patterns. You can choose on a 3D printed part. Is it solid? Does it have different infill patterns? And then the density of that pattern. And that's going to change the material properties of the part also in a way that's going to be for the same load. You could have two different infill patterns, and one would fail at a different point than the other. So in summary, you can't solely rely on theoretical analysis to set dimensions and shape and materials, et cetera, of a 3D printed part. And with a metal part, you can get pretty close to doing that. Or even you can fully do that. And so with 3D printed parts, you're using prototyping to figure out when something's going to break is important. That said, thinking analytically can inform your experimental prototyping, your empirical prototyping. And that's what we're going to talk about how it can do just that in the rest of the video. All right, so we're going to talk about two types of snap fit scenarios. The first one being a cantilever snap fit, which you can see the sketch on the left. This is a picture of the snap coming down, and then if you push it in, it'll have to push around the material and ultimately go into that hole, that notch into the blue piece of material there. And if we were to draw this in 2 dimensions, here's how we might draw it. You can see the orange cantilever, and then the blue piece of material is represented by that little blue rectangle on the right. Now, as we start pushing the cantilever to the right, it's going to reach a point. Now the cantilever is dashed because it can't be in that position. It can't be in that position because it's going to interfere with the blue piece of material. And so the snap's going to have to bend. And the snap will bend down like this. And then if we keep pushing it to the right, then it'll reach a point where it makes it to that notch, to that hole in the blue material, and the snap fit will snap back up because it has that elastic property where it bends and then it bends right back to its original position because it's in that linear region and it hasn't gotten to a point of its ultimate tensile strength or flexural strength and breaking. One of the big points here is that in a situation like this, the moment, which I'll tell you what that is in a moment, no pun intended, causes failure in a long, slender beam like this. So let's break this down and see what I'm talking about. Well, this all starts with the idea that the snap fit needs to deflect a certain amount, and we'll represent that with the variable y is the amount of deflection. And I want to draw something on the right called a free body diagram, where the snap fit is now just all floating in space, and we're going to draw the forces and other things that are acting on it. And the force that's actually on it is from getting pressed down by that blue material. And what causes that force? Well, it's the deflection. Because the cantilever is having to deflect, it's bending, and that bending is causing a force to be experienced on the cantilever beam or the cantilever snap fit. Now back to our free body diagram, this cantilever beam isn't going anywhere, it's just bending. And so it has to have another force on it somewhere to keep it in place. And the only other place it can be is back on the wall or back on the base of it where it's attached to the main part. And it would be an equal amount of force there so that the forces cancel each other out. Now, these forces are acting across a length. And because they act across a length, you could imagine that they could make this part spin, like a rotate around. And so the way we model that in a free body diagram is that there has to be something countering that. And the thing countering that is called the moment, M. And the moment is simply the force times the length. Failure, in the case of a cantilever beam, is caused by the moment. And more fully stated, failure of a long, slender beam like this one is caused by the stress, which is produced by the moment. Second point, related points, I'm calling it point 1A. As the deflection gets bigger, the moment gets bigger. That is, too much deflection can cause failure because we know that the moment is the thing that causes failure. Well, let's go back and look at what I'm talking about. Here's the same diagram we had from before. And if you increase the amount of deflection, you're going to have a larger amount of force acting on the snap fit material. As you increase the amount of force, we can see from the equation at the bottom, the moment equals force times length, you're going to have a greater moment. And as you increase the moment, that's going to increase the stress related from that moment, which increases the chance of failure. So the idea here is that you want to design the snap fit so that the deflection is not so big that the part breaks. And if you have the deflection be too big, the snap fit can snap right off, which is something that you don't want it to do. All right, now a related point, so it's point 1b, is that the moment is actually maximized at the base, the place where the snap fit attaches to the rest of the part. And because of that, your snap fit can get narrower towards the tip. Let's go ahead and see what I mean by that by returning to the free body diagram. And make a plot below the free body diagram of the amount of the moment. And I'm going to kind of start thinking about this point out where the force is applied. So the force is applied out here. And so I'm drawing a dashed line down from that. So the magnitude of the moment, the maximum magnitude for the moment is F times L. We know that from earlier. But the magnitude of the moment at any point along the beam, starting from this dashed line where the force is applied, moving to the left, if we were to call that distance x, just how far away are you from the force that's applied, the moment is just F times x. And so at the point where the force is applied, the moment's 0. And at the base where it's attached to the rest of the part, it's F times L. And in between in between those two, it's just a linear relationship. And that it's negative on this plot is just a convention. It doesn't matter for the point of understanding whether the part fails or not, and understanding that the maximum moment is experienced at the base where the part is attached to the snap fit. So maintaining that thought, let's see what this looks like in 3 dimensions. I mean, your snap fit looks kind of like that, right? Well, you actually don't need that much material at the tip as you do at the base in order to prevent failure. We talked about stress being the thing that causes failure, and stress is something that is kind of a force per area of the cross section. And so you could have a smaller cross section towards the tip than you can at the base. It's like, for instance, a plot, a shape kind of like this or something like that for the snap fit could work given the idea that the moment's getting smaller and smaller and smaller the further and further you go towards the tip. All right, we're on to a new point. That's exciting. Elasticity occurs with relatively small changes in Y, relatively small strain. And if you get past those relatively small amounts of strain in a brittle plastic, it's just going to break. Not massive strain, small strain. And you start with small strain and build up to larger if necessary when you're designing a part, would be my advice. So remember, the amount that you're actually moving the part is the deflection. And this amount of deflection, sort of roughly, that's like, okay, good. For PLA, the material that we're dealing with, if you were to design a part that required this kind of deflection, not good. There's no way it could do that. It would just snap. It would just break. So that's just knowing that we're working with a brittle plastic. And in order to stay in that elastic region, it has to be relatively small amounts of strain. So start small. If you find out that it's not strong enough to hold the part, like the little snappy part isn't snappy enough, then maybe make it so that you have a larger deflection. But starting with too big of a deflection can lead to places where just the part breaks. And not in terms of analysis, but let's talk about why the shape of the snap little point actually it matters. And this has a lot to do more with the usability side of it from a human point of view. So here's drawings you've seen before. Snap, gets pushed in, the cantilever snap gets pushed in, and ultimately it snaps into place. Well, I'm going to draw this bottom one out to be in 3 dimensions a little bit more, just so you get a sense of what's happening here. Now, imagine trying to remove this part that you snapped in, this orange part. If the idea is that you snap it in and you never take it apart ever, this might work okay. If the idea is you need to be able to snap it in and out pretty regularly, then it looks like it's going to be pretty darn hard to pull that snap back so that it'll be released. So with that in mind, you could consider other kinds of shapes, like a softer shape, something a little bit more like this, that could allow the part to not only be easy to snap in, but just by pulling back on the orange part, it would have more of a curved surface that then it could kind of it could deflect and be pulled out. And it's just a matter of understanding what your snap is for. Is it for a permanent connection, or is it for a connection that you need to be able to put in and put out just by inserting and then pulling back out left and right on this drawing on the snap. All right. So as I would think analytically as you're designing a snap fit, if you're designing one that's a cantilever style, certainly the length of the snap fit is something that you know is a parameter that you need to be thinking about. Uh, the depth, so like the third dimension that I've drawn on a few of these drawings, like how wide do you want it to be? And then like, does it get narrower towards the tip? How much narrower does it get? That's a question to have. All the cross sections I've had have been rectangular, um, so you could consider other things than that. Certainly the snap height, so how tall is the bump that it has to, so ultimately how much deflection has to occur in order for the snap to be snapped in, and then the shape of the snap. We saw how that could affect whether, the use case, whether you want to ever be able to take this snap off again. This shape of the snap might want to be different. Now, this isn't an exhaustive list of parameters you might want to consider when you're designing a cantilever snap fit, but it's some of the ones to get you started. And with the idea that, so certainly the material is a consideration for design also, but in your case where in this case, you're using a PLA 3D printed material. Another important consideration is that you need to avoid, if you can, any sharp corners in your parts in any areas that have high stress. And you can do that really easily by putting in fillets. Why? Well, sharp corners lead to stress concentrations, and a stress concentration can make a part fail, even though it has a load when it shouldn't be causing that part to fail based on analysis alone. When we're working with elastic parts like these snap fits that deflect, and that deflection is what causes the force, and that force is what causes the moment, and that moment causes the stress that causes the failure. Sharp corners lead to stress concentration, which means an elastic part can fail with a lower amount of deflection. And if you had rounded corners, that means that your elastic part can have more deflection and not fail. So here's a pretty simple example where you have this blue part that could be pushed in to the orange one, and you can see how the snap fit might work in that case. This is drawn like, looks like 2 cantilevers where they each have a force on the end of it, where you see these 2 beams. This could be an annular snap fit that's round also, but the principle would be the same. And we know now that the places of maximum stress are down here at the base of these beams. And look what we have, 90-degree sharp corners. The fix for this is fairly straightforward. It's just to put in fillets, which will give you rounded corners and reduce the stress that's caused for a given deflection. All right, now we're going to shift to a different type of snapping. And in this case, it's snapping around a circular rod or pole. So here we have our rod that we're looking like straight into, you can imagine, or straight down on. And let's see what the situation is that we're generally talking about. Here's this orange part. That's a plastic part that we're going to just push around this rod, and it's going to snap when it goes around it. We can define this angle, which I'm calling theta, and for this drawing, it's at 45 degrees, which is how much of the material that you're kind of pushing around the rod, how far does it extend that material? I'll show you some other examples. I mean, just to get the kind of idea across, if theta was 90, then there wouldn't be any snapping at all, actually. It would just kind of push up against there. This would not snap fit on. Theta was 80, then it just kind of barely has a little bit of material that extends past the halfway point of the rod. And what if theta were 10 degrees? Then it really wraps all the way around it. And you could see how, like, when you're designing the orange part to snap around this blue rod in the drawings, that one choice you have is, well, what should our theta be for this? Well, let's talk about some considerations about what your theta should be. And that theta really is driving how much your part has to deflect when it is being inserted over the rod. In some ways, that is, this is a lot like, a couple of cantilever beams sticking out that are each going to have to deflect, one at the bottom side, one at the top side, in order to be pushed over that rod. A variable that's useful to define here, I'm going to call h, is just the distance from the center line up to the point that the material extends to on your part. And now I've just shown the part on the bottom, making the part now in a little bit of a lighter line, a thinner line, because I want to draw the thicker line to show what would happen when you're actually inserting or removing this, when you're pushing it over or pulling it off of the rod. It might look something like this, where the two little prongs that are sticking forward need to deflect in order for the part to extend over the full diameter of that rod. So here's H on that drawing, it's still there. And the maximum that the prongs of this part, of this snap fit part, need to extend to would be the diameter of the rod, d, divided by 2, or the radius of it. So the deflection is just the difference between these two. The diameter of the rod divided by 2 minus h, which is how far the snap fit part extends. So we've already established that this is somewhat like a cantilever beam, but in this case, the beam is curved as it wraps around the pole. All the points from before apply, but performing the analysis by hand is harder because the beam isn't straight anymore. But so we're not going to do that, performing the analysis, but we are going to see about some of the same points and how they could apply and how they could affect your thinking when you're designing such a part. So I have our 3 different examples on the bottom. And the deflection, if we had theta set to 90, is going to be 0 because the part is designed such that the prongs never have to extend in order to insert it or pull it, pull it out. It never wraps past that midpoint of the rod that you're trying to wrap it around. So you would never, the max deflection is 0. Now at 80 degrees theta, we might want to ask, like, do we think the deflection would be required to put that on? Would it be less or more than the deflection at 45 degrees? And you'd be like, oh yeah, it's probably less, right? It doesn't have to deflect as much. And you're right. What it is, we'll get to in a minute. And then out for 10 degrees on the far right, that's going to have to deflect a massive amount in order to get over the rod because it's almost closed on the other side. The H for it is very small, and the diameter of the rod hadn't changed, right? So it's going to have some massive amount of deflection, which would be larger than the amount of deflection for 45 degrees. How much? Can we determine how much the tip has to deflect for a given theta? And we're, in this case, going to turn to just geometry and trigonometry, identifying this triangle from the drawing above. You can see that for an angle of theta, the hypotenuse is the radius of the blue circle, which is the diameter divided by 2. And then the original height of the plastic part when it's not deflected is h. Well, y'all know that the sine of theta is opposite over hypotenuse, so that's h over d over 2. And if we want to solve for h, then we just move the d over 2 to the other side. So it's d over 2 times sine of theta. Ultimately, we want to know about the deflection. The deflection from earlier, we know, d over 2 minus h. Now we can just combine these two equations, and we know that the deflection is d over 2 times, in parentheses, 1 minus sine theta. Let's go back and apply that. Let's check out how this actually applies in practice. So for a theta of 45 degrees, we would be able to calculate that the amount of deflection is going to be 0.146 of the diameter of the rod. All right. And if we calculated this for theta equals 90 degrees, we can see that it is indeed 0. 1 minus 1 is 0, and so the deflection is 0. Taking our two other examples, at 80 degrees, we can substitute the values in, and at 10 degrees, substitute the values in, and we see that the deflection is definitely smaller at 80 degrees than it was for 45 degrees, and we see when theta is 10 degrees, the deflection is almost 0.5 d. It's almost, the full radius, but 0.413 d when you actually calculate it out. And interestingly, as you progress from a snap at theta equals 90 degrees, which really isn't a snap at all, it just kind of pushes up against. But as you start decreasing theta, so you have more and more material, wrapping around this rod, for every degree that you keep reducing for theta, initially the deflection, it changes very small, but for every degree additional that you wrap around your snap fits, the deflection is going to increase more and more and more as you get down further and further. So a 1 degree change from 81 degrees to 80 degrees for theta is going to cause a certain amount of change in deflection. If you were to do a 1 degree change from 46 degrees to 45 degrees, it would be a larger change in deflection because you're further wrapped around. And that's how the sine works, right? The shape of the sine function works. So if you're designing for something snapping over a rod or a pole, you certainly need to think about theta because theta drives the deflection. And deflection is a critical thing to be determining uh, for any kind of a snap fit situation. I say you also want to think about the tolerance. And what I mean by that is if the rod that you're trying to snap around has a diameter of D, what should the diameter of the inside of the prong that's going over be? Should it be identical in D, or should it be a little bit bigger or a little bit smaller? When I say a little bit, let's just say that your diameter of your rod was 2 inches. You know, should it be 2.01 inches? Should it be right on 2 inches? Should it be 1.99 inches? That's what I mean by tolerance. The tolerance of the diameters. The depth, of course, like the thickness of this, how much does it go into the page? Um, the cross-section shape, the little prongs that stick over could be getting, narrower towards the tip, just like we saw for the cantilever example. And the fillet radius, and particularly that fillet that I have the arrow drawn towards, you know, that's a place where there's high stress. And so, how much of a fillet do you want to have there? Hey, it's summary time. We started talking about material properties generally, and then in particular about 3D printed fused deposition modeling, in particular of PLA. And you certainly can learn a lot from thinking analytically to inform prototyping with 3D printed PLA. But because 3D printed PLA and layered FDM in general is so different from the neat and clean textbook behavior, you really need to use some prototyping to help drive your design and not rely solely on textbook pencil and paper analysis. We spent a long time on the cantilever snap fit with the idea that the amount of deflection drives how big the moment is, that the moment drives when the part fails, when it snaps off, which is something you don't want it to snap off, and the moment's largest at the base of the snap. The deflections you're talking about should be relatively small for elastic snap fits. This isn't something where you're bending at 90 degrees. It's really small, just a few degrees that you want to have that cantilever snap fit bend such that it doesn't break off. The snap shape matters, certainly for usability, and then fillets in all sorts of places. Cantilever snap fits, just one of them, can help avoid stress concentrations. And then finally, we talked about snapping around a rod in particular, which in the abstract is similar to a cantilever beam. Um, and because deflection is so important with cantilever beams, it's important to be able to understand the deflection associated with snapping around a rod. And you can derive that from the geometry of the rod and using a little trigonometry too. All right, that is it. Now get out there and design those snap fits.